So let's take one example. x1, x2, xn are IID. Normal 0, theta square. Find the MRIE of theta to the power b. Let us take theta to the power b for convenience under the following loss function. So first of all, we have to see under what kind of transformations this is invariant. So the first two things which I have done is a location family or a scale family. So let's try to see whether it belongs to a location or a scale family. So if I look at the joint PDF of x1, x2, xn, what is that? That is product I is equal to 1 to n because they are independent. 1 by sigma, which is theta, root 2 pi, e to power minus 1 xi square by 2 theta square. X belongs to Rn. So what does that becomes? This is nothing but one by theta to the power n, 1 by 2 pi to the power n by 2, e to the power minus summation xi square by 2 theta square, which is basically, in fact, you can write down this as directly from here, this is same as product I is equal to 1 to n so this, so the only thing what you have to do is you have to see whether this is of the type f of x1 by theta, x2 by theta, and xn by theta or not. So this is the same as 1 by theta to the power n, f of x1 by theta, xn by theta, because that is the PDF corresponding to the scale model which we considered. So where f of t1, t2, tn is nothing but 1 by 2 pi to the power n by 2, e to the power minus 1 by 2, summation I is equal to 1 to n ti square. So what you saw is your joint PDF of x1, x2, xn is belonging to a scale family, 1 by theta to the power n, f of x. Because if you try to see what was the distribution function over there in the scale model, distribution function of f of x1 by theta, xn by theta. So if you have to get the PDF corresponding to this, you have to differentiate it n times with respect to x1, x2, xn. Each time you get 1 by theta, so that theta to the power n good comes, and the derivative of that with respect to x1, x2, xn, which I am calling that as small f. Okay, so this belongs to a scale family. So the problem is invariant under group of transformations GC, C positive, GC of x1, x2, xn is same as C of x1, x2, C of x. No issues with this. So I know that easiest approach is first to try to find out a complete sufficient statistic. What is a complete sufficient statistic in this case? From your last course, you know that summation xi square is complete sufficient statistic. Is summation xi square is scale invariant? So let us apply c times x1, c of times x2, c of xn. So xi square becomes c square times xi square. So that will not work, but because I want c to power b. Right? So what I do is I consider delta naught x to be summation I is equal to 1 to n xi square to power b by 2. Then what is the delta naught of cx1, cx2, cxn? It becomes c square xi square, and when it comes outside, b by 2, 2 gets cancelled, and you get c to power b. Which is same as c to power b delta naught of x. So that means this is invariant. And this is also a function of complete sufficient statistic summation I is equal to 1 to n xi square. And in this case, because we know that z is ancillary, so I know what is the MRIE. So by the result which we did, MRIE of theta to power b delta star x, which is delta naught x, expected value of at theta is equal to 1 of delta naught x. There is no conditional distribution because my delta naught is a function of a complete sufficient statistic. E theta is equal to 1 delta 12 x. So I need to find out what is expected value of delta naught x or delta naught square x. So which is same as, so I can find what is expected value of delta naught to power, let us say, Rx under theta is equal to 1. Now note that under theta is equal to 1, summation xi square has a chi square on n degrees of freedom. So delta naught x is nothing but chi square on n divided by b to power 2. So this would become expected value of chi square n to power b by 2 and r, so it becomes br by 2. Right? So which is easy to calculate, which is nothing but 1 by PDF, I'm trying to write down 2 to power n by 2, gamma n by 2, 0 to infinity, t to power br by 2, e to power minus t by 2, t to power n by 2 minus 1 dt. Which is 1 by 2 to power n by 2, gamma n by 2, 0 to infinity, this becomes t to power n plus br by 2. N plus br by 2 minus 1 e to power minus t by 2. Now for this integral to exist, this quantity should be positive by the property of the gamma function, because e to power minus t, integral 0 to infinity, e to power minus t, t to power alpha minus 1 is convergent only when alpha is positive. So what I need is n plus br by 2 should be positive. So my b, and it should happen for r is equal to 1 and r is equal to 2, because I'll need delta naught x and delta naught square x. So that means r is equal to 1 should be positive. So that means n plus b by 2 should be positive. So what I do is n plus b should be positive. and n plus 2b should be positive. So that means b, n plus b should be positive, and n plus 2b should be positive. So that means b should always be greater than minus n, or b should always be greater than minus n by 2. So b should always be greater than minus n by 2. Otherwise, so I'll be able to estimate theta to power b provided b is greater than minus n by 2. And then in that case, it becomes 2 to the power n plus br by 2, gamma of n plus br by 2 divided by 2 to the power n by 2, gamma n by 2. Now you can find out what is d star x. Is delta naught x, which is xi square to power b by 2. And then r is equal to 1 divided by r equal to 2. So this is common factor. This would get cancelled. R is equal to 1 gives me 2 to the power n plus b by 2, gamma n plus b by 2. R is equal to 2, which is equal to delta naught square x, 2 to the power n plus 2b by 2, gamma n plus 2b by 2. So you can simplify this. So this is one way to find MRI. If one wishes, one can use directly the formula for the squared error loss function. What would be the so alternatively, delta star x is nothing but 0 to infinity f of x1t, xnt dt. There was t to power n plus b minus 1, I guess, yeah. Then 0 to infinity t to power n plus twice b minus 1 f of x1t, xnt dt. Right? This is the ready-made formula which we derived. Now, if one wishes, one can get the same estimator from here. So let us see what one get using this. So this is same as 0 to infinity t to power n plus b minus 1. Joint density of x1, x2, xn. In this case, what was my f of t1, t2, tn? 1 by twice pi to power n by 2. E to power minus 1 by 2, summation ti square by 2. So summation ti is xit, so summation xi square t square. Same thing over here, 0 to infinity, t to power n plus twice b minus 1, 1 by 2 pi to power n by 2, e to power minus 1 by 2, summation xi square t square. Now solving this integral is not difficult. So one can do, so this gets cancelled. So what do you get? This becomes 0 to infinity. Let me just simplify it a little bit. T to power n plus b minus 1. E to power minus t square by 2 summation xi square dt divided by 0 to infinity t to power n plus twice b minus 1 e to power minus t square by 2 Note that range of integration is 0 to infinity. So t and t square are one-to-one function, or in other words, since the range of integration is 0 to infinity, t square is a one-to-one function. So I can make transformation as t square by 2 summation xi square as some another variable, so that I get everything in terms of a gamma function. So I make the transformation t square by 2 summation xi square, let us say as z, right? Or in other words, t as square root of 2 by summation xi square and root z. Is that okay? Square root summation, yeah. So dt is nothing but this term times 1 by 2 root z. So this becomes 0 to infinity t to the power n plus b minus 1. So 2 upon summation xi square half. So n plus b minus 1 n plus b minus 1 by 2 z to power n plus b minus 1 by 2. All that becomes e to the power minus z. Jacobian becomes square root of 2 summation xi square. What is the dt? dt is this times 1 by 2 root z. So this has comes 1 by 2 root z. 0 to infinity 2 by summation xi square to power n plus twice b minus 1 by 2 z to power n plus twice b minus 1 by 2 e to power minus z, this Jacobian term 2 times summation xi square into 1 by twice root z dz. Okay, so what does that become? So n plus b minus 1, so first let us try to see this. N plus b minus 1 by 2 goes away. So I make it here minus n minus b. So it becomes b by 2, right? So it becomes summation xi square by 2 to power b by 2, right? I guess, yeah. This and this are taken care of. This will get cancelled from the both numerator and denominator. This 2 will get cancelled from both numerator and denominator. And then the remaining thing left is 0 to infinity z to power n plus b by 2 minus 1 e to power minus z dz by 0 to infinity. That becomes z to power n plus twice b by 2 minus 1 e to power minus z dz. These are constant which involves gamma function. So this becomes summation xi square by 2. I hope I have not made any calculation mistakes. And this becomes gamma of n plus b by 2 divided by gamma of n plus twice b by 2. So one can get this from alternate formula also. So you can sometimes one can use both the approaches. Sometimes it is more easier to use one approach. As I said in the beginning, in situations where complete sufficient statistic exists and its distribution is tractable, then you take delta naught to be an invariant estimator, which is a function of a complete sufficient statistic, and then you go by the approach 1, which I just explained over here. Alternatively, you can use this formula, but you will get the same answer. So this was all about scale invariant estimation. So let me stop over here. So what we have done so far is we have done a location invariant estimation, where only location parameter is there. Only one parameter is there, which is a location parameter. A variant of this was situation where I have only one parameter, but that parameter is a scale parameter. So for example, when I dealt with a location case, I dealt with a normal theta 1 kind of a situation. So normal theta 1 means variance is known. There is only one parameter, theta, which is a location parameter, in the normal case, which turns out to be mean. Then scale case could be something like this. My mean is known, so I can take it to be 0, but variance is unknown, theta. So that is a scale kind of a. But there will be situations where you have a location parameter as well as a scale parameter, and both are unknown. So like a normal mu sigma square kind of a situation, where mu and sigma square both are unknown. Now those situations, when I am dealing with a location scale family, that means there are two parameters, one of them is a location parameter, one of them is a scale parameter. I have to find a suitable group of transformations under which location scale family remains invariant. And then I can repeat the same thing which I did for the location case and the one which I did for scale case. So that is what we'll do in the next couple of lectures. So we'll deal with location scale invariant estimation. So that we'll do in the next lecture. Thank you very much.